and the finished project in Hong Kong Harbor. One of the interesting parts about doing these iconic buildings is that they appear in stamps and in money and so forth. So we have a collection of these. Actually, one year for this project, the government had printed $20. That's divided by about 3. So bills, and so we got a whole bunch of them, nice brand new ones, and we included them with a year-end note to all of the friends of our company. Shanghai World Financial Center, 492 meters high, and the original design looked like this. And several ramifications took place after that. One is that the mayor of Shanghai was very unhappy with the round hole at the top, because this is a Japanese developer, and the mayor said, well, it looks too much like the rising sun of Japan, and we will not have it over the city of Shanghai. Bill Pedersen, the architect, is a very skilled talker and very quick thinker, and he said, no. He said, there's a bridge across. So he sketched this bridge, which I was unhappy with, because I thought a much handsomer bridge could be done, but the mayor, once he accepted the idea of the bridge, which he did, he said, well, once I've accepted it, that's it. You build that one. But the design with the new mayor changed again, and now the top of the building has this shape, which now has no resemblance to the rising sun of Japan. And here you see the temporary works in place as that opening is being created. Now, in 1995 or thereabouts, I'm not totally sure about the date, the building was supposed to be 460 meters high, and the design was finished. The original design for the structure was done in New York, a kind of a schematic design. That went to Japan and was completed by a big Japanese steel company who did structure, mechanical, electrical, plumbing, architecture, everything. And the work was sent out for tenders. And a Japanese steel company came to us and said, well, is there a better way to do it? And we said, yes, there is. And we proposed an alternative design. And right then, the project died because of the Asian financial crisis. When it came back alive again, and Mr. Mori wanted the building higher, and he wanted more floor area in it. But the problem was that all the piling had been put in place for the lower, smaller building. And Mr. Mori went to various sources and was very discouraged. And then he remembered the alternative design that we had done, and it's a very long story, but in any event, ultimately we ended up with the commission to design the building. And to give you an idea of the scale, here you see on the left the Petronas Towers, which for a short while was the tallest building in the world. The Jinmao Tower, which is the tallest building in the PRC, the People's Republic of China. 2 IFC, 2 International Financial Center in Hong Kong. Taipei 101, which again was for a short while the tallest building in the world. And then the Shanghai World Financial Center. All these things are very complicated. Now, I believe the Shanghai World Financial Center has the highest roof and the highest occupied floor, but it still doesn't be the tallest, because there's this one and then there's that other building in Dubai. So this was the original design. Very good design. Uses wide, closely spaced columns on the outside of the building, and a deep spandrel, and to all this to resist these great wind loads that I mentioned. And this was our proposal, to eliminate all of those columns and use just small columns on the perimeter, and to use diagonal bracing. And this is a model, not of the whole building, but just of the primary structure, which we had constructed to explain to the wind and seismic experts of Japan how the structure worked, because it's difficult to two-dimensional drawings to explain three-dimensional structures. And here you see the building in the wind tunnel. The structure is designed for earthquake and wind, and the two act very differently on a building. This is just an example of one. We call it a time history. This is a real measure of a real ground shaking taking place at some other place in the world. And we just take that earthquake record, and in our computer, we make it happen in Shanghai. Perhaps for those of you who are not engineers, a more easily understandable is, we call it a pushover curve. You imagine that somehow you just lean against the building and push, 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 push. And this starts to yield, and then that starts to yield until ultimately you push it over. You have two images there. So the rare earthquake is right here. And the first hinge that takes place, as the first yielding, is in the wall construction of the services core. It's a very safe hinge to have. And then a series of others, hinges in the diagonals, again very safe because it's not in the columns that are holding up the building. And finally, even more wall hinges. And then ultimately the first hinges in columns. These are the dangerous ones. But you see, this is at a lateral displacement more than twice the design displacement. So this building is very, very safe. And to describe all of the redundant and robust features would take the entire lecture. Wind design is interesting. We track all the windstorms within an area of about 500 kilometers. And they look like this. This is a track of all the windstorms that we could find. And then we take so-called tropical stage windstorms, which are pretty common. And then the typhoon stage windstorms. And you see, in the entire history, no typhoon ever passed through Hong Kong. But we call it a Monte Carlo simulation. We pretend that all of these windstorms have a certain probability of landing over a typhoon, over Shanghai. And so we're able to generate a kind of artificial wind climate that is representative of perhaps 500 or 1,000 years of records. Okay, we'll go on. Now, there are other facets in very tall buildings that are worth thinking about. One of them is lightning. Now, normally you put a lightning arrestor on top of a building and you feel pretty good about it. The ones that you see and probably here in Bergamo are like little spikes. Very tall buildings we use something closer to a flying saucer, a kind of a disc. But in very tall buildings, the lightning can be generated below the top of the building. So you have a whole different problem. You have to start dealing with lightning arresting along the side of the building. And that's just one example of hundreds and hundreds of different problems that separate the very tall building from a normal multi-story building. A very tall building is an entirely different creature. So anyway, we have pictures of the construction of the Shanghai World Financial Center. And this is the picture of one of the columns in the corner of the building. When you get pretty high, it's a wonderful feeling. Well, depends on the person. For me, it's a wonderful feeling. For you, it might not be. Anyway, we built up and up and higher yet and almost finished. And that's the way it looks today. And in fact, later this month is the opening ceremony for the building. So how did we do? Well, this is a comparison of the total weight of the building. This is the original design on the left, and you see we were able to build a taller, larger building that weighed less than the original design, and that's one of the many reasons why we could reuse the existing foundations and build a bigger building on top of them. And then Dubai is a wonderful place, so you all read about the fantastic buildings in Dubai, and I wanted to show you a couple of images. This is a site for a building intended to be a little more than 1,000 meters high. To get there, you leave your hotel. I have to tell you, in the summertime, it gets up to 50 degrees or even a little hotter. In the summertime, you cannot go to the beach because the sand is too hot to walk on and the ocean is too warm to swim in. But in the summer, it's wonderful. In any event, you get an all-wheel drive vehicle and eventually you find your way to the site, and here it is. And to prove it is actually a site, drilling equipment, actually making borings for the foundation system. And the interesting part about this is that when you get on top of your all-wheel drive vehicle and look in all directions, nothing but sand. Nothing. No buildings, no roads, no nothing. And this is or will be a waterfront site. Incredible. So I think I should probably stop there because my hour is up. But if you have questions, I'd be happy to answer them for you. I'd be delighted to, actually. And, here she is. So I have to say, that in audience it's often very difficult to get people to ask questions. And I often wish that I could just point at someone and say, you must ask me a question. Okay. Is it on?
Bene, grazie Mr. Robertson. Apriamo il dibattito e iniziamo con le domande, se ci sono domande in sala. Vedo già delle mani che si alzano, quindi diamo la parola.
Good evening, Mr. Robertson. I'm Christian Brumbilla from University of Studio Bergamo. Two simple questions. What kind of dumper system do you use in your buildings? And the second question is, have you ever used color facade with a color changed with the external condition? And how much is the radiation solar gain? Thank you.
I didn't understand the first question. Could you repeat that? I missed one word. What kind of
damper system
damper system? Okay,
system.
I see. All right. Well, in very tall buildings, particularly if they are slender, in the wind, they oscillate back and forth. Well, all buildings oscillate, but tall buildings more than others. And the oscillation is not in the direction of the wind, but it's usually, most of it is transverse to the direction of the wind. And to reduce that deflection, we use devices, various kinds of devices that either resist the motion of the building or consume the energy of oscillation of the building. The first building where this was done deliberately was the World Trade Center, using a device, a viscoelastic damper that we designed. We invented, I guess is the right word for it. They are now marketed from Japan. Also, another quite inexpensive and reliable device is called a sloshing water damper. That is, as the building moves, water in tanks passes through a kind of grid, and as it does so, the energy of that water is dissipated, changed to heat, and that reduces the swaying motion of the building. So those are the two types that we have used. The third kind of less obvious is the shape of the building. And the first major project I showed you with the building with the notched corners is a technique for producing aerodynamic damping. It's intrinsic to the shape of the building itself. Some shapes are very bad aerodynamically, a triangle, a pure triangle being an example of one, and others are much better. So one can deal also with the aerodynamic side of it. There are various other kinds. In the Shanghai World Financial